I'm going to talk to you today about Fury. Are you all sitting comfortably? Nobody said a word. So how many people here know something about Fury? A little bit. Okay. No, is anyone using it? Nobody. Yeah, silence. So I would love you to start using it. And I'm going to be giving a workshop on Wednesday about Fury, and that will hopefully give you an opportunity to start using it. It hasn't been widely publicised, but it's been bootstrapping for a while now. And I'm going to talk to you today about some of the ideas in Fury, how it came together, the motivation behind some of those. I'll talk about some of the more specific problems it faces, including some of the problems it introduces and then resolves. Fury came about partly as an idea at the back of my mind which I'd had for several years. An idea which I thought I'm probably never going to have enough time to work on this. It's a nice idea, it'll never happen. I have a lot of those. And then I went to Northeast Scala Symposium in Boston in 2018. And I was chatting to Rob Norris, who you probably know very well. And he was working on another project of mine, Magnolia. We were looking to integrate Magnolia with Doobie and make Doobie's generic derivation faster. And he found an issue that meant we couldn't continue. And on the flight home, I decided that it would be a great opportunity. I'll be up at 10 kilometres in the air with no distractions, just me sitting in the airplane seat and with my laptop, nothing to do but hack on this project. I love that. I get a lot of work done. I'm very productive on flights. And I was excited about getting this bug fixed so that Rob could start using Magnolia with Doobie. I got into the air, fired up SBT, and it failed with a stack, some sort of stack trace. And I had no idea what was wrong with it. It was working fine when I was on the ground. As soon as I got in the air, it was not working. I tried a few things. I don't really know how to use SBT. I didn't know how to fix it. I couldn't do the work I'd planned to do, and I was angry. So this message, which I left with Rob a couple of days later, I decided that the best thing to do to solve this issue was to write a new build tool. Rob is still waiting for my ping. I think over the months since then, or year and months since then, the idea has evolved a little. It's developed. I've had new ideas, greater ambitions, and what I would like to do is not just write a new build tool, not just write something which has already been done before, which solves this or makes or mitigates the existing problems we have. I would like to take a more revolutionary approach. I'd like to, as I've said here, change the way people build and also distribute and run code. That is part of the goal for Fury. It's wildly ambitious. I don't believe it's over-ambitious, though. I believe there's an opportunity here to throw away a lot of the baggage we've collected over many years, start afresh with some new ideas, some new concepts, and some new ways of doing, of building, developing, and maintaining builds. And I think it's an opportunity to give Scala users not just a build tool that is comparable to those we see in other languages, but the best build tool and the best experience of developing and sharing and working with builds of any modern language we have. It's ambitious, but I think it's possible. So I'll talk through a few of the ideas that went into Fury. The first of those is the decision to use source dependencies. Now, there's some debate over whether source dependencies or binaries is the better solution, or whether even some halfway house between the two, tasty, for example, would be better. I've decided to go with source dependencies primarily. And the motivation behind that is that I really don't trust the tooling we have at the moment to correctly link up code, bytecode, that has been compiled at different times, that's been compiled separately. How many people have seen a linking error at some point when trying to run code? So no such method error or class not found exception. These are occurring because different binaries from different places have been put together on the same class path, and they don't match up. The methods that are being called simply don't exist or have the wrong signature. This happens because there's a failure in the tooling to construct that class path correctly. Now, that I say it's a failure in the tooling, it might be a failure in the metadata that's used by the tooling to link those things together, but the situation arises because we're trying to combine things which have not been tested and compiled together. Now, source dependencies gives us an approach whereby we can guarantee, by compiling everything in the same process, that there will be no possibility, modulo compiler bugs, there'll be no possibility of any sort of linking or runtime error relating to a mismatch. You have the sources there. You don't have to work with this projection of the sources, the binary that has lost some of the detail that's maybe an inaccurate representation of the APIs in the source code. So by having all the sources together at the same time, by passing them through the compiler will check for us. It will offer the guarantees that the code we run will not fail with a linking error, because runtime is the absolute worst time to find out about that. We would much rather have a compile error, can't find the method. Okay, we'll go and look at the source code, we'll go and fix it. That's much easier to work with than the situation where we run it and then sometime in production a rarely used method gets called or attempted to be called and it fails. So Fury, in defining the sources it will use, can refer to a Git repository and an exact hash within that Git repository. Now, there's some advantages to this. It means we don't have to rely on binaries being published here in advance of using them. Now, is Bill Venners here? Oh, it's a shame. I've seen him this morning. So I don't know if you know, when a new version of Scala gets released, as happened a few months ago with Scala 2.13, a process kicks off very quickly, involving a few key people. The people who design libraries and maintain and publish libraries that are widely used, which include Scala Test and includes also Scala.js, Scala Check. These libraries need to be available for anybody who depends on them to publish their libraries. So the whole ecosystem is being held back if these libraries don't become available for the latest version of Scala. You've probably experienced this by some less widely used library that you use not being available for 2.13 when you want to use it. Has anyone experienced that? Yeah. The whole ecosystem, the whole multi-billion-dollar industry that we use, that we work in, is waiting on a few key people. One of them is Bill. One of them is Sebastian Duren, who publishes Scala.js. These key people have the potential to hold up the entire industry. Now, that's not right. I don't think that burden should be left upon those people. They're open source developers. They're giving their free time. In the case of Bill, I believe he pays someone to do the releases for him. I don't believe that he should be paying someone out of his own pocket to ensure that the very rich ecosystem and industry that we're in can move smoothly. What I would like to do is to make it much easier for anybody to publish, for anybody to start using or start compiling their own version of Scala Test or Scala.js as soon as they want to. I want them to be able to do it with let's say someone wants to experiment with modifying the compiler. They want to try Scala test with a modified version. If you have to publish everything first as binaries before you can use it, before you can combine these things together, it makes those experiments very expensive. I'd like to reduce the cost of those by allowing people to very quickly combine disparate collections of sources together and do ad hoc compilations to check how things will work. That's something which we can do with source dependencies, and a build tool which is focused very much on those source dependencies will allow us to do those ad hoc experiments. Another thing I did differently with Fury was I decided not to have a build file in the traditional sense. I didn't want to have a build file that you edit with an editor. I took what you may describe as the Git approach. Now, if you have a Git repository, inside there, the file on your local hard disk, there will be a .git directory, and inside there's some data. And maybe you've had a look at that data. Maybe, if you're brave, you've tried editing it directly. Has anyone done that? Yeah, okay, right. You are brave. But that's all that Git does. It's modifying that data in the repository when you run a command. It just calls the command looks in the directory, has some expectation about what it will find, and makes changes. And that's basically how it works. You're not meant to edit those files. They're not designed to be used that way. Fury takes a similar approach. There is a build file, but you don't edit it directly. You run commands which query it and which can modify it. Let's do a little demo. Can you see that?
Huge.
That was huge, yes. Now, I didn't practice this at all. So live coding in a keynote, which has never been practiced. This is let's see what is here. This is a project which I use to build the Scala World website. So I've got some sources in here, and you can see there's some things like sandwiches.csv. That was your lunch at the weekend. That was an output file. If I run Fury, this will try and download some stuff, and it will compile a reasonably complex graph of things to produce at the end this is going to run the module at the bottom, which you can see is called MailShot, which I was using to send out emails to most people, but some people didn't receive them. I'm sorry. The reason is that there's a bug in my code, probably. So this is the Scala compiler doing its thing at its usual pace. I haven't fixed that yet. Come on, let's see some progress. There we are. So this is building my Scala World module, and then when it gets to the MailShot, it's not only going to compile that code, which is it's basically a script which gets some data from a database and then sends emails out, but it's currently disabled, so you won't get any more emails. That's running at the moment, so I'm just going to kill that. That's the experience of running Fury. Now, I can run a command like that, and you see I've got tab completion, and I get a list of the modules there. You can see the dependencies between them. You can see around the middle column there are some brown text. Those are the directories containing the sources that will be compiled. You can see the choice of compiler. I'm always using the Scala compiler. And you can see that these are mostly libraries. There is an application at the end. If I wanted to add a module, I can add a module like this. I can give it a name, which will obviously be foo. And I can choose a compiler. Let's choose Java for a change. And I can make this an application. So that has created a new module. If I list the modules again, you can see somewhere up there is foo with an arrow to the left of it showing you that that is the current module. Now this is the typical way you interact with Fury. It's colourful, it's interactive, you get tab completion. I believe this is a very nice way of interacting with the build tool, making changes, querying it, developing and evolving the build. That's all I'm going to demonstrate because I haven't prepared anything else, and I'm terrified it will go wrong, which would be very embarrassing. So that is a different approach from I think every other build tool I've used. Now the build is defined as nothing more than data. Now if you use some other build tools like Bazel or SBT, they actually contain code which is executed. It is maybe compiled and then run. And code is unfortunately harder to work with than data. Code needs to be converted into something the computer understands before it can be easily used. There's a transformation step. With data, we basically have all the information there very fast, very easily, which can be very easily analysed and modified, and this gives us a lot of benefits that we wouldn't have with a dynamically generated graph of dependencies. The challenge with that is to define a data structure which is able to encapsulate all of the things we might want to include in our build. So that is the cost of using data. It means we can't, there are some things we can't do that we would be able to do with code, but the benefits we get allow us to do structural analysis. We can do various checks on the graph that we're running, building, compiling. It's simple, it's fast, and we can analyze it easily. And Fury is actually nothing more than a tool for manipulating this data structure. So having designed the data structure to represent builds, Fury is just a tool for changing that. When you run a Fury command, it modifies a file that contains that data structure, a serialization of that. Every Fury command reads the file in, either prints some output or makes a change immutably, and then saves that file back. Now that's a very simple, that makes it a very simple tool in many ways. And if we just have a data structure, that actually means that if our build is just some ADT, that means that effectively we can refer to any build just by a hash. We can refer to another build just by, as long as we've got access to the full definition of the build, we can refer to it by hash. And if the build is different, if the build changes, that's a different hash. It means that we can refer to one hash and that will always be the same build. And builds are composable. So I can have one build which refers to another, and that build can refer to another one. They form a tree, and Fury will combine these to enable us to produce effectively our own mono repo or mono build by composing them together and producing, as you saw here, the graph. Well, that's a very simple graph because there's no dependencies. If I select that, then this is a graph like this, which has been composed from projects such as Honeycomb. That's one of mine. In fact, these are all mine. Kaleidoscope. The ones that are defined, it's these web ones that are in the local project. But essentially, it's one build that builds everything from nothing but a Scala compiler, through to a final jar file. So composability is good, and we can just grow these builds. There might be some work to do later with resolving conflicts, and I'll talk at length about that. But effectively, we have imports from one build to another. We can refer to projects that are defined elsewhere. And the way Fury does that is using a hash. Now that's great, as long as we can convert that hash into the actual build definition. If we have everything locally, that's also great, but we want to share builds with other people who are distributed around the world, potentially. And Fury is going to use a protocol called IPFS. How many people know anything about IPFS? The Interplanetary File System, which is a very grandiose name. It's a protocol and peer-to-peer network for storing and sharing data in a distributed file system. IPFS uses content addressing to uniquely identify each file in a global namespace. I think it's not just global, but universal, I think, given the name. Connecting all computing devices. It's very ambitious. There's basically two APIs that IPFS provides. If you give it some content, some data, it will give you a hash. If you give it a hash, it will give you the content. Mathematically, it's not a one-to-one mapping, but effectively, the hash is large enough that it is. The chance for conflict is basically zero. So we can refer to some data by its hash, and as long as IPFS can find that over its peer-to-peer network, and it's very fast at doing that, it can resolve hashes very quickly using a Merkle DAG, I believe. We get a very nice way of quickly distributing builds. All I have to do is give the data to IPFS, I get a hash back, and I can share that hash with somebody else. And Fury will allow us to do that automatically. It'll be integrated. You won't have to interact with IPFS directly. IPFS has a few nice features. It's inherently distributed. It claims to be adaptively resilient. So if a node disappears, or if a whole collection of nodes disappear, then it's able to recover from that. It's able to route you to the data that may be stored in different locations. It can store the data multiple times if it's commonly used. It can find the fastest route to accessing that data. It can download from multiple sources at the same time. These are all nice properties to have, and IPFS is sufficiently self-contained that I don't need to worry too much about how that works, because I basically don't understand it. It's magic. And it's immutable. If I put some data onto IPFS, then it's always there. I have the hash to access it. So effectively what we get is a global, I should probably say universal, database of builds indexed by hash. That's very nice. That gives us a lot of scope for working with builds more easily, more directly. We can always get a build from IPFS, so it's a little bit like a cache, actually. There's a little bit of work to be done to make sure that some data that's put onto IPFS doesn't get lost. So I could add some data from my laptop to IPFS, I would get the hash back, and then I turn my laptop off, and there's no route to getting that data. So if I want the build to be available universally, we need to do some things to make sure that there will always be a machine that has that. And IPFS provides those tools. They are still evolving, but this is something that Fury will require as it evolves. But I'd like to go through a little worked example of how you might interact with Fury using IPFS. So imagine this. We have a build for our project, which the current project is just called dot, effectively. It's your current directory, or your current workspace. Now let's imagine that we depend on the type level build. Now when I say the type level build, I'm imagining a build which we're composing into ours which contains definitions for projects we might like to depend upon. We're not depending on them, but we want to make them available for us to depend on. Let's say I want to use Circe. Now, the type level build is itself composed of other builds. It's composed of Circe, Doobie, and many more. There's a great ecosystem of libraries there. So the Circe import, this is another build here, which we access effectively through type level. So we're going from our project to type level to Circe. That depends on Shapeless. And then there is a build, let's imagine, for Shapeless, which has no dependencies. The way Fury would view that is using hashes. So this is the hash of the current build. It imports from this hash, which would get resolved over IPFS, to this build here, which we happen to know is the type level build. That imports these two. This one is going to be Circe. That imports Shapeless. So apart from the difficulty of remembering what these hashes are, hopefully you can see the sort of structure that we have available to us. This little arrow here I've included in the table to indicate what I think of as the current build. So all those commands you saw me running in the demo are being run in a particular directory based on the context of what the current build is. We're currently working on our workspace. But we can actually navigate builds. We have all of the information available. We have all of the data that defines those builds at our fingertips. It's all within this global database of builds. And we can navigate that. We can run a command like Fury layer select, and I can type in the path to Shapeless, for example. So I'm sort of pointing up the tree, type level Circe, Shapeless, and I've changed my focus. So my focus is now this hypothetical Shapeless build. So any command I run, listing the projects, listing the modules, that will be as if I'm running it directly on the Shapeless build, even though I'm in my working directory for my project. So there is some state which exists in that directory, which is our current focus, and having typed this in, I'm now focusing on the Shapeless build. So if the hash of that is this one here, I can make some changes. I can add a module to Shapeless, just so I feel like it. I can maybe upgrade to a more recent version. I can change the sources. Any change I make will change the hash of the build. So that hash has changed. Consequently, Circe, which depended on Shapeless, has a different is now pointing to the new hash, which means that the Circe build's hash has also changed. This one has changed as well to point to the new Circe build, and the type level hash has changed, and consequently we're now working with a different hash. Now that's absolutely correct. It's a different build because it has a change somewhere deep within it. What's nice is I'm able to modify Shapeless or Circe or any of these builds just by navigating into them. I don't have to clone any repositories. I don't have to work out what commands to run in order to make the change. I certainly don't have to republish those builds or any binaries. I just make the changes. Anything that needs recompiling will then be recompiled using Bloop, which is the build server, the compiler server for Fury. And you can, when Jorge gets here later, you can find out more about Bloop. For now, it just gets a very honourable mention. Having done that, I can then point back. I can select my current layer again, dot, and I'm back where I was before. So I believe this gives us a lot more power to work with builds, to make changes, to experiment, to tweak things, to get better fluidity in how we work with different dependencies, complex dependencies. And there's a need to do this. Anyone who's had conflicts on their class path will have discovered this need to somehow resolve these. So making that process of resolution easier is going to be a benefit. I'll give you a brief overview of some of the concepts in Fury, because I've mentioned things like layers, modules, and projects without really explaining them. A layer is a little bit like a build. It contains a collection of projects, often only one, but maybe many. You import projects or define projects in a layer. So it may have no projects defined in itself, but it may import others. So the type level layer, for example, would import probably projects from other layers. Each project contains one or more modules. A module is a unit of compilation. You can't compile half a module. But you can define dependencies between modules, you can compile one, and it will build the entire tree in order to compile that. So a module is the unit of compilation. Projects have a requirement that I enforce, which is that you can't have two projects with the same name in the same layer. So if you have two imports which import projects that are different, this is a problem. And it should be a problem. You shouldn't have two different versions of Shapeless or two different versions of Doobie in your layer at the same time because we don't know how to resolve them. Layers, or builds if you like, are the unit of distribution. We don't distribute one project, or we don't publish one project at a time, we publish an entire layer. So often you'll have a layer with just one project, but you could potentially publish many at once. Those, I think, are the three main concepts that are useful to understand when making sense of a Fury build. Let's look at an example. So here are three projects you're probably quite familiar with: Circe, Spire, and Doobie. They're all type-level projects. This white rectangle is meant to represent a layer. The green squares are projects, and the blue dots are modules. So this is the structure. And these arrows pointing up here are indicating, these arrows up here are indicating an import. So Doobie needs to import from Shapeless because it depends upon it. So you import first. We will show you the dependencies in a second. Likewise, Circe also depends on Shapeless, so it needs to import it. These modules in here are going to need to depend on this module in Shapeless. These orange arrows are indicating what those relationships are, those dependencies. So Circe has two modules, hypothetically, and one of those depends on Shapeless. Doobie has two projects, and these links between the modules. Spire actually doesn't depend on Shapeless. So this is a probably not uncommon setup. Having defined all of those, we could additionally combine a few of these, Circe, Spire, Doobie, Monix as well, into another layer, let's say a type level layer. It defines nothing itself, so it's empty, but it does import all of these as well. And transitively it imports Shapeless. So if you had your own workspace and you were to import the type level layer, or if the type level layer wanted to import if the community build wanted to import the type level layer, combine it with Scala test, you could quite easily import the community build and you would have access to the build definitions, so that is hashes referring to the builds, for all of these projects and others which I just didn't display in the diagram. That's something which I hope the community can come to maintain. In our workspace, we probably want to define some projects of our own to build. That's the mental model I'd like you to have for how builds are structured. There's a little detail which I should share with you as well, which is that the dependencies between layers actually point to something called a schema for each layer. A schema is like a variant of a layer. Typically, the schemas in a particular layer will be mostly the same. So for a project like Circe, it will build for Scala 2.11, Scala 2.12, 2.13. Those are subtly different builds. They do require different things. They might include, for example, some shim source files in order to allow Scala 2.13 to compile with mostly the same code as Scala 2.12. They will certainly, in this example, contain a different choice of Scala compiler. Maintaining those builds, maintaining different schemas, shouldn't require us to change each schema individually as if it's a completely different build. So that's why I've lumped them together in a layer as a different concept called schemas, because they are essentially, all of the details in a schema are essentially the same, apart from a few little things we want to tweak. So Fury is designed to make it easy to maintain those builds. When you deviate from one build, you create a new schema, but it's a small variation. Most things will be the same. And when you import from one layer to another, you specify the schema you want to use. That's just a name. Scala-212 is probably a typical name you'd use. You might have a name like latest, and by convention that would use the latest Scala compiler. But that's a choice for the build maintainer to use, to make. Now, does anyone know what this is? What this represents?
Dependency conflict.
A dependency conflict, diamond dependencies. Though I've drawn the arrows this way because rather than a diamond, it looks a little bit more like a mushroom cloud, which I think is more appropriate. Here we have the type level layer, which depends on which imports from Doobie and imports from Circe, and both Doobie and Circe import from Shapeless. But the definition of this build here is using a hash which points to a different version. Now, we don't know why it's different. The hash is different, and that's all we care about. It could be something that's irrelevant. It could be some minor detail that makes no difference to the binary that gets produced at the end. But that's not our concern. They are different, and we need to resolve this. This is a conflict. Now, we've got a couple of options. We can navigate, if we are maintaining the type level build, we can navigate into the Doobie build, point to this hash over here instead of this one, and then Fury will know that actually this is pointed to the same definition, and that's no longer a conflict. If you have the same hash twice, it's fine, no problem. We could do the same thing on the Circe side instead. And it's just a matter of navigating to the build, changing the thing that's different, or maybe even copying from one to another to resolve the conflict. There might be some other more drastic approaches you need to make. You might want to end up splitting Shapeless into two different versions and giving them different names. You'd be forced to give them different names simply because there is this constraint that we have a one-to-one mapping between a project name and a project definition. But that's all possible because we have access to the entire tree of builds for our project. This is where I think a lot of the work will go on with maintaining builds. And I hope that the tools that Fury will provide will make that process easier. And also easier to share. So a lot of people do all this work themselves or within their company. They put a lot of work into getting their nicely curated class path with all of the right versions matching, and hopefully everything just works. And as soon as someone wants to upgrade something, there's more work to be done to use that more recent version. But people keep it private. What I also want to do is lower the barriers to publishing and sharing builds, especially for open source software. And this is where the distribution tools come in. With a simple command like Fury layer share, it will put the data onto IPFS, and it'll give you a hash back. I've given it a Fury scheme there. And that can be used by anybody else immediately, anywhere around the world. They can access your build by cloning it, in the same way as you would clone a Git repository. So you've just published and shared a build. You've shared it with a name that's probably not very easy to remember. That's cloning it. You could also import it directly, give it a name, my import, whatever it is, with that hash. What I'd like to do, this is a little bit further off, but hopefully by the end of the year I'll have this working. Some sort of tooling for associating a name with a particular build hash. It's basically a lookup. We want to be able to look up type level /shapeless /v 2.3.3, something like that, and have that resolved to a particular build definition. And we could even do things like give you tab completion on this, so you could directly select your whatever you want to import. And this wouldn't necessarily need to be immutable. This would not be stored directly in your build definition, because this doesn't necessarily point to the same thing today as it points to tomorrow, especially if it's something like shapeless /latest. So this is merely a convenience for specifying a build we want to use. It's not it's not something that would be stored in the build file. The process of releasing, I've got some work ongoing on this, and that will be as simple as running a command like fury release, specifying a version number, and that will talk to Maven Central. We put an open PR to merge that, and you would be able to do things like splice your jars in some, or split your modules between certain jars and publish those as separate entities on Maven Central or elsewhere. I want to make it easy to publish binaries as well, even though I don't really believe binaries are the long-term solution. They're going to be around for a little bit longer, so that's why that's in there. And there's a few more upcoming features. We have IDE support contributed by Justin Kieser using BSP. So Fury acts as a BSP server, and I'm really grateful to Justin. Are you here, Justin?
Hi.
So Justin will talk a little bit later about BSP, I think. 10:25. Not long. I need to hurry up. And Fury acts as a BSP server, and that will interact with IntelliJ and Metals. If a lot of people are building the same or running the same builds, compiling the same code, it would be useful to cache those binaries, and that's something I'm looking at, so we don't have to rebuild things that we trust as compiled binaries. So distributed caching is something that I'm looking to add. I mentioned jar splicing and releasing. Forking sources. Now, it is often useful to experiment with making little changes to projects we depend upon. Now, if anybody's done this with Maven or SBT, the approach I used, and I think Dale has told me there's a better way, but it's not particularly straightforward, I don't think. The approach I've always taken is to clone the repository for my dependency, make some changes inside that, publish it locally. There might be other projects in my dependency tree which I need to do the same thing for, updating them to the snapshot each time, republish locally, publish locally, change my dependency, and then I can experiment with what that new version, or what those changes actually, how those affected my project. But Fury, when it resolves a build, has all of those sources locally. It's going to compile everything locally. What we can do is just simply say, well, let's fork those sources out of the central hidden storage into a local directory on your hard disk, and modify them directly. It's as if your build has changed to point to the local sources. So every time you make any changes there, Fury will just rebuild them, and it'll rebuild the entire tree as necessary. That, I think, is it's going to allow some nice options for publishing and sharing ideas and testing them on downstream projects. It'll make it very easy to experiment with maybe a change to shapeless that could potentially have impact on downstream projects. The barriers for making those changes I want to reduce to something minimal. Now I'm running out of time, so I will mention what I think is probably the most important feature that is currently missing: stability. I don't have sufficient stability of connections and connected to BSP, stability of the source code, coexisting with things like metals on the same system. We have a lot of issues here, and this is my number one priority before I make any public announcement about a release of Fury. This, I hope, I've seen a couple of pull requests which have come in from Virtus Lab while I've been organising the conference. Virtus have been helping me hugely with this, and I work in a team at Virtus Lab in Kraków in Poland, who also develop metals. So the work that hopefully a lot of you have experienced with using metals to compile and edit Scala, that's developed with cooperation with the Scala Centre at Virtus Lab in Kraków. I sit with that team, and we're going to make this work. It's going to be very reliable very soon. Once that's done, I will add a few more features, and we're not far away from a release that I can recommend to people. So, very briefly to summarise. Too long, didn't listen. I have big ambitions for changing, building Scala, compiling Scala, maintaining and running builds. Watch this space. Pay attention to Fury. I hope that I can make a change for everybody here in how you go about developing Scala, working with dependencies. I hope I can reduce the amount of time you spend having to manipulate class paths and resolve dependencies. I hope that I can improve the quality of your development experience on the building side. This is my goal. This is what I'd like to achieve. And I would be really interested to discuss any of these ideas with anybody here over the next couple of days. So I hope this sounds exciting. It's exciting for me. In about a week, I won't have a conference to run, and I can focus on this a lot more. And I'm looking to run through until Christmas, focusing entirely on Fury. So I'm excited for this opportunity to get along the final few weeks worth of development, and to produce a build tool which I think has the potential to change the Scala ecosystem. That's my ambition. So thank you for listening.